Hi everyone, today's lesson will be on sum and difference of cubes. This is the type of factoring that many of you haven't learned before. Unless you're in pre-calc, you might have already seen it. So in order for us to be successful with this type of factoring, we're going to need to review certain vocabulary. As we know, sum means to add and difference means to subtract. We spoke about perfect squares before, but now we're going to talk about perfect cubes. A perfect cube is the result of three of the same numbers or variables multiplied together. So for example, 1 is a perfect cube because it's the result of 1 times 1 times 1. Just like 1 is also a perfect square because it's the result of 1 times 1. 8 is a perfect cube because it's the result of 2 times 2 times 2. 27 is also a perfect cube because it's the result of 3 times 3 times 3. 64 is a perfect cube because it's the result of 4 times 4 times 4. 125 is a perfect cube. It's the result of 5 times 5 times 5. And so are the rest of these down here. Now let's move on to variables. The first perfect cube variable would be x to the third. It's the result of x times x times x. Then we have x to the sixth because it's the result of x squared times x squared times x squared. Then we have x to the ninth, x to the 12th, and so on and so on. Now, here's something I want you to notice. What do you notice about the exponents of all perfect cube variables? When we talked about perfect square variables, we said that they were all even. So, are these all odd? The answer is no, they're not all odd. Look at 12. 12's even, so is 6. So, what are they? You should be saying that they are all multiples of 3. So let's write that down. Multiples of 3. So any perfect cube variable will be a multiple of 3. Now what do I mean in this next part? What about its cube root? So for example, if I wanted to write, I'm just going to write it up here, the cube root of, say, x to the sixth, that's this guy here. The definition of a cube root is what thing times itself 3 times gives me x to the sixth. And the answer would be x squared. What would be the cube root of, say, x to the ninth? Look over here. What thing 3 times gives me x to the ninth? The answer is x to the third. So what do you notice about its cube root and its perfect cube inside? What's the relationship between this power 9 and that power 3? When we did square roots, they said they were half. So what is 2 in relation to 6 and 3 in relation to 9? You should be saying that it's a third of this power. So 6 times a third is 1/2, or how about divided by, right? 6 divided by 3 is 2. 9 divided by 3 is 3. How about the cube root of 12? If you take 12 and divide it by 3, you get 4. So we want to say cube root is 1/3. 1/3 of the power. Or you could just say divide by 3. Okay. So these two formulas for how to factor sum and difference of cubes are here below. They are not given to you on a reference sheet. You eventually are going to have to memorize them. And with practice, you will be doing these much faster. So basically, we are going to say that if we factor a to the third plus b to the third, its factors underneath will look like this. A plus b times a squared minus ab plus b squared. So we would have this expression and factor it below. So that's what this is saying. So let's show that it works. Let's show if we multiply this times this, we get this. So we would distribute everything, or we can use that box method. I think I'm going to do that. For those that want to double distribute, that's fine as well. So a, b, a squared, negative ab, b squared. So in this box right here, I'm going to go across. This box would be a to the third minus a squared b, ab squared, ba squared, negative a b squared, and b to the third. So let's see what happens. Let's look at our diagonals. What happens with these? Well, we have a squared b, a positive and a negative. These are going to cancel when we add them. A squared, negative ab squared, ab squared, a positive and a negative. These are going to cancel also when we add them. So we are left with a to the third plus b to the third. So this works every time. Now why don't you pause the video and see if you can prove that a to the third minus b to the third, this is a difference of two perfect cubes, that if we factor it, we'd get a minus b, a squared plus ab plus b squared. So please pause me. Okay, so you should have did it something like this. Here's a and negative b. Here's a squared ab, b squared. This would be a to the third, a squared b, ab squared, negative a squared b, negative a b squared, negative b to the third. So again, on my diagonals, when you add these and when you add these, they're going to cancel. And all you're left with is a to the third minus b to the third. So what we've done is we've just proved that these two formulas work for when factoring a sum of two cubes and a difference of two cubes. Okay, now I think we're ready to put it into play to practice some examples. Okay, before we get into the more complicated examples, I'd like to review a few things first. You don't have to write any of this down. If you would, you can pause the video for now until you get a piece of paper to write it down. Okay, so I just want to show something. If I take 3 to the third, and something to the third means 3 times 3 times 3. What do I get? You should be saying 27. Now, what does it mean when I take 3a to the third power? It means take 3a and multiply it 3 times. 3a times 3a times 3a. So we take the coefficients, 3 times 3 times 3, we multiply those, we get 27, and then we take a times a times a. Remember, when we're multiplying exponents that have the same base, we keep the base, which is a, and add the exponents, which is 3. Okay, same thing for here. We've got 4ab to the third. Multiply 4ab 3 times. Let's multiply 4 times 4 times 4. You should get 64. And when we do the a's, remember to add the exponents, we get a to the third. And we multiply the b's, we get b to the third. Okay, next example, if I want to multiply x, or raise x squared y to the fourth to the third, that means multiply it 3 times. So what would we get here? X to the 6th, y to the 12th. So what I wanted you to notice is a pattern. When I just took a number and raised it to the third, I did 3 times 3 times 3, I got 27. When I did 3a to the third, the 3 was raised to the third to get this 27, and then so was this a. This a was raised to the third, but how did I get a to the first to the third? What am I doing with these two things? You should be saying multiplying them, because 1 times 3 gave us that 3. Now let's look at this example. 4ab to the third. The 4 became a 64, and how does that happen? By taking the 4 and raising it to the third. And then what happened to the a's and the b's to get a to the third, b to the third? Well, this a had a power of 1, and this b had a power of 1. If I take 1 and multiply it by 3, so this 1 times this 3, I get that 3. Take this 1 times this 3, I also get that 3. Alright, so now let's look at this last example here. Since there's no coefficient other than 1, we're just taking the 2 and the 3 and the 4 and the 3 and multiplying them. So watch, 2 times 3 gives us that 6, and 4 times 3 gives us 12. So this is stuff that will come in handy when we start factoring. Okay, when we factor sum and difference of cubes, we always want to think SOAP. And what does SOAP stand for? SOAP is going to stand for same, opposite, always positive. So if I want to factor a sum of two cubes, the first parenthesis is going to have the same sign. That's what S stands for. So the first parenthesis will have the same sign. Same. Then we will have the next symbol or the next sign be opposite. So same, opposite, and the last will always be positive. So again, same as this sign, opposite, always positive. So if we want to take a difference of two cubes, we're going to say that the first sign is going to be the same. So S for same. Same. The second sign is going to be opposite. Same, opposite, and then the last will be always positive. So that's what SOAP stands for. If we want to write down what is same, opposite, always positive. Okay, so let's look at the first example. We have a to the third plus 27. So this is a sum of two perfect cubes. So let's write it as the form something to the third power plus something to the third power. Well, the first one, a to the third, is already written as something to the third power. And now we need to just rewrite 27. 27 is the result of 3 to the third. So now we have our a and we have our b, and we're just going to model this equation. So we're always going to have two pieces. And here is going to be your a, and here is going to be your b, just following along here. So a and b. b is the second thing that's being cubed. The sign is the same. Then we're going to say, in this parenthesis, a squared. So this is the a, and we're going to square it. So a squared. The sign is now opposite. Remember, it goes same, opposite. Now we're going to take a and b and multiply them together. So a is a, 3 is b, so 3a. And last but not least, take b and square it, or take this 3 and square it. So that would be 9, and that sign is always positive. So it's going to be same sign here, opposite, always positive. And what we did was follow along with this formula here. Okay, let's try example 2. First step is always want to write it as something to the third power minus something to the third power. So a to the third is just a. Now what number to the third power will give me 125? You should be saying 5. So now this is a difference of two perfect cubes, so we're going to set it up this way. So it's going to be in here a and b. So a and 5. And then the sign is the same. So again, same, and then it'll be opposite, always positive if you want to set it up. And then what's going to be in here? In here will be a squared. Here's my a, so let's just write it, a squared. In here, the middle will be my ab, so 5 times a is going to be 5a. And then the last will be b squared. So my b in here is 5, so 5 squared will be 25. All right, why don't you pause the video and see if you can do example 3. Okay, so it's already written as something cubed plus something cubed, so it's a sum of two cubes. In the front parenthesis, it's going to be a plus b, so it'll be x plus y. In the second parenthesis, remember from up here, it's going to be a squared, so the first one squared would be x, so x squared. Opposite sign, same opposite, so opposite now a times b, so x times y. And then always positive would be the last sign, and it's going to be b squared. So here's y squared. That's it. Okay, example number 4 is where it gets a little tricky, because we need to write this as something cubed minus something cubed. So this goes back to that page that I did before. How do I get 125, or how do I write a number and raise it to the third power and get 125? We did it up here. So we've got a 5, but now how do I get that x to the third? We're going to need to put a 5x, Because remember, when I raise 5x to the third, it's 5 to the third, which is 125, and then x to the third. That would be my a value, if you want to write that. And then for 27, we know it's 3. 3 to the third is 27. And if I made it 3y, then I have 3 to the third is 27, and y to the third is y to the third. So maybe if we want to write that, this is my b. Okay, so let's set it up. So inside the parentheses here, the sign we keep, so same, opposite, always positive. So I just set it up. And if we follow, again, this same pattern, it goes a and b. So a is 5x and b is 3y. The first parenthesis is a squared, so 5x squared. Let's be careful with that. That will be 25x squared. So remember, I'll put it off to the side, 5x squared. That means 5 squared, which is 25, and then x squared, which is x squared. So that's how I got that first term. And then the middle term will be a times b, so ab. So this times this will be 15xy. And then the last term will be b squared. So b squared is 3y, and 3y squared would be 9y squared. Just like we squared 5x. That's a 2. Okay, number 5 is a little different, because when I look at number 5 right away, I see that there's a greatest common factor. And if you remember that flow chart that we've been discussing in class, the first thing we always want to do is check for greatest common factor. Now, the reason why I didn't do that with these first 4 is because there wasn't a GCF. I should have mentioned it, but I wanted to make sure that you had the sum and difference of cubes down. So now we're always going to check, like I said, for GCF first. So we could take 2x to the third and 16 and divide it by 2. So I'd get x to the third plus 8. So now, in here, I can factor this because this is a sum of 2 cubes. So let's write it the way that we need to. It's going to be x to the third plus, what thing to the third gives me 8? You would say 2 to the third. So now we're going to use our knowledge of sum and difference of cubes. And we're going to remember to put that 2 on the outside when we're done. So remember, the sign is going to be the same, opposite, always positive. So what goes here and here? You should be saying a and b, or a and b. So x and 2. What goes here is a squared, so x squared. What goes in the middle term is a times b, so 2 times x, which is 2x. And the last term is b squared, so 2 squared, which is 4. Okay, that's it for that one. Number 6, first things first, is there a greatest common factor? Can I divide anything by 64 and 8? You should be saying 8. So let's divide everything by 8. We'd be left with 8x to the third minus y to the third. So again, let's rewrite this as a sum of 2 cubes. This is easy. This would be y. What would this one be to get 8x cubed? You should be telling me 2x to the third. So again, here's my a, here's my b. This is a difference of 2 cubes. So let's set it up. Same, opposite, always positive. And again, don't forget to put that GCF out at the end. So it's going to go AB. So A is 2x, B is y. Here is going to be a squared, so 2x squared or 4x squared. In the middle is going to be a times b, so 2x times y would just be 2xy. And the last one would be b squared or y squared. And that's it. All right, let's look at example number 7. Example number 7 is a little funny because it's almost a sum and difference of 2 cubes. I say this leading coefficient bothers me. I say we take that out first. So -1 would be my GCF. I'd be left with a to the third plus 8. I like this a little bit better because it's a little clearer that this is a sum of two cubes. It would be the sum of a to the third plus 2 to the third. So we'll set it up the same way we have been all along and make sure we bring down our GCF, which is a -1. So my A goes here, my B goes here. Let's set up our signs. Same, opposite, always positive. So the first one would be A and 2. What goes here? You should be saying A squared. What goes here? You should be saying 2A, or A times B. And what goes here? You're saying B squared. So 4. Okay, let's look at example number 8. Is there a GCF? Well, let's try 3. And since there's a negative here, let's try -3. So -3, we're left with x to the third minus, you should be getting 64 y to the third. So let's set it up as a sum or difference of two cubes. So 64y to the third. To get 64, you need to cube 4. And to get y to the third, you need to cube y. So that's what that would look like. So again, we're going to bring down our parentheses. Same, opposite, always positive. Don't forget to bring your GCF. And now I think we're ready. So A goes here, or x. B goes here, or 4y. And then here is a squared, so x to the second. Here goes AB, so this times this, 4xy. And the last term would be b squared, so 4y squared would give you 16y squared. Okay, why don't you try the last two, pause the video, and resume for the answers. Okay, these should be your answers. Please come in with questions tomorrow in class.